sines. The nice thing about 8.1, 8.2, 8.3, it's all stuff that you should have seen in pre-AP geometry before. So some of this might come back to you. You might still have this somewhere, like in the back of your minds, or somewhere in your memory stored some way, somehow. Some of it might look familiar to you, maybe. So it's stuff that we've seen before. So the other thing is, if you haven't seen it before, if it's taught at the sophomore level, or at the, not the sophomore level, because some of you are sophomores right now, but if this is taught at the geometry level 2 years before precalculus, you should be able to handle it, no problem. And we're not going to go over everything in these sections. We're going to go over mainly just solving triangles. So we're going to concentrate mainly on solving triangles. There's application problems, which I will give you a few application problems. It's just drawing pictures, so word problems. But then there's also extra problems on how to find the area of triangles if you don't have a base and a height. So there's other ways using trigonometry to find the areas of triangles given limited information of a triangle. So the question then arises, when can I solve a triangle that is not a right triangle? For a right triangle, we're already given one of the angles, which is 90 degrees, as long as I have two other pieces of that right triangle, an angle and a side, two sides, and two angles, something like that, then we can find the rest of the right triangle. We can solve it no problem. So we need three pieces for any triangle, for the most part, to be able to solve a triangle. So there are right triangles, which we've already mastered those. You would just use inverse trigonometry for the hardest cases. And then we have what we call non-right triangles, or the word for that would be oblique triangles. So this weird word here, oblique, which we've seen that word used before, but for different things, like oblique asymptote, when we're talking about the asymptotes of a function. Mainly rational functions is where we've seen those. But we call a triangle that's not a right triangle an oblique triangle. So that's a superset of two types of triangles, which we already understand as acute and obtuse. But if you lump them together as just non-right, we call that oblique. So there are three situations where we can expect a unique solution given three pieces of information. So if we're given two sides and the included angle, that's one of those situations. If we're given, two angles and the included side, that's another situation where we can expect a unique solution. And then when we're given three sides, that's another situation in which we can expect a unique solution. Now, if we're just given three sides, I don't think we can use the law of sines by itself to figure that one out. The first two cases, we can use the law of sines, no problem. The third case is probably one that I'd recommend using, which is what we're going to see in the next section, the law of cosines. So I'm not going to go over too much of this. What I do want to concentrate on is a proof of the law of sines, or a derivation of the law of sines. There are two cases, because there are two types of oblique triangles, an acute triangle and an obtuse triangle. So I've never really followed this before, so I'm going to try doing that here on video. I normally move this over to the side and I'll draw a triangle and I'll try to prove it myself. I've never followed this, but they have one here outlined for me. Why not use it? You know what? Nah, I'm going to go ahead and do my own. Yeah, so we'll do our own. So I'm going to go with case 1. And then there's case 2, when we have an oblique, or an obtuse triangle. Now, it turns out to be true for right triangles as well, so there's a third case, right triangles, but it's so easy to verify just using trigonometric ratios. It just boils down to a quick trig problem. So we would consider that like a trivial case. So case 1, when triangle ABC is acute. Oops, and I wrote A twice. So we have an acute triangle. Try my best to draw an acute triangle. So say something like this. This is A, B, C. So all of those angles are supposed to be less than 90 degrees, and it kind of looks like I did okay. And then we also have side lengths, little a, little b, little c. And hopefully the placement of A, B, and C, and little a, b, and c are obvious here. So little a, b, and c have to be opposite of the uppercase A, B, and C, respectively. So we're trying to show, so we're trying to prove, so the theorem for that triangle, sine of big A divided by little a, it's a ratio, is equal to sine of big B divided by little b. And that's also equal to sine of big C divided by little c. Proof. What I'm going to do is I'm going to copy and paste this triangle because I'm going to need to draw it a second time. Let's see if it lets me do that, which I hope it does. I'm going to try to recreate it down here, see if it lets me. That's not too bad, so I'll leave it, probably leave it there. So first part of the proof, I'm going to try to show that sine A is equal to sine B or sine C, one of those two. And I think with the way that I drew it, I might have to make sine A and sine C equal to each other. So we'll see how that works. How would I do it where, yeah, either way. So what you do is you draw an altitude from one of the angles. So an altitude is a straight line segment that will intersect the opposite side at a 90-degree angle. And we call it an altitude because the measure of the altitude is what we call the height of that triangle, h. So I'm calling that h. So then what next? The reason why we do that is because we want to try to calculate sine A, B, and C. So why did I draw an altitude and how did I know to draw an altitude? One, it's because I've proven this a bunch of times. Two, it's because the only way that we can calculate sine A, B, or C right now is by using right triangles. So this is a way of forcing a right triangle into the picture. So now I have two right triangles. Triangle AB, we can call this D, this point here D, and then triangle CBD, which it's kind of cool how that worked out. But anyway, we can say that sine A, and what's A? A is this guy right here. And if I wanted to try to calculate a ratio for sine of A using a right triangle, I'm using triangle ABD. So I'm only looking at ABD. So sine A, if you remember correctly, opposite of A, which in this case is H. Right, that's the opposite of A. On a right triangle, not the acute triangle, the bigger one, the inner one that makes a right triangle. So H over C, because C is the hypotenuse of that right triangle. So sine of A is equal to H over C. So I'm supposed to get sine of B as well. Problem with sine of B though is B is not part of that triangle. So I can't use B right now. So that's just not going to work the way it is. Whoops, and I didn't mean to do that. But so somewhere like that. What I can do, however, is calculate sine of C. So sine of C, I'm going to have to look at the other right triangle, triangle CBD. So that one, sine of C, is the opposite of C, which is H still, divided by A, because A is the hypotenuse of that other right triangle CBD. So if you look at those two formulas, sine A and sine C, there's an H in common. I'm supposed to show that sine of A is equal to, or sine of A over A is equal to sine of C over C. So these two quantities are supposed to be equal to each other. And how can I form those two quantities? The way that I can do that here is by isolating H in both of those two expressions. So how do I isolate H in that situation? You multiply by C on both sides and you get H equals C times sine of A. Same idea here. You're going to multiply A on both sides. So multiplying A on both sides will tell you that H is equal to A sine of C, big C. So then what next? I don't see a letter H at all in the theorem that we're trying to prove, so I'd like to eliminate that letter. And the way to eliminate, you set these two equal to each other. So if H is equal to that and H is equal to that other thing, those two things should be equal to each other. So these two together should tell me C sine of A must equal A sine of C. And we're almost done. Now these ratios have an A on the bottom and a C on the bottom, so I might want to divide these. So divide by C both sides, and I get sine A is equal to A sine C over little c. Same idea here though, we're going to divide both sides by A. So these two cancel, because these two canceled earlier. And then we get sine A over A must equal to sine C over C. And that's 2/3 of the proof. These two are equal to each other. Now, in order to complete the proof, I must show that one of these two is equal to sine of B over B. So one of those two must be equal to the middle one in order for us to complete the proof. Now we can do that easily by drawing my altitude from some other angle. We drew the altitude out of B. This time let's draw it out of A or out of C. Doesn't really matter which one. I'm going to draw it out of A. So if I draw an altitude out of A, basically it's the same mathematics. Now it's just C and B that we're comparing to each other, and we should get that sine of C over little c equals to sine of B over little b. And you could try doing that, no problem. I can't call that h anymore, since I called this quantity h up on top. They're not the same quantity, or at least they're not supposed to be the same. Or we're not expecting them to be. So I'll give that another letter, maybe k. So then k is the altitude of that triangle looking a different way. So we'll set it up. I can calculate sine of B using the inner triangle. We can call this D again. BAD, triangle BAD is a right triangle. So then out of that triangle BAD, sine of B opposite over the hypotenuse, and this is the hypotenuse, letter C. So this is K divided by C. Now if I wanted sine of C, opposite of C, so sine of C, opposite is K divided by hypotenuse. In this case, that's little b. That's for triangle CAD. And those are the two ratios I want. I follow the same mathematical procedure here, and I should get that sine of B over little b is equal to sine of C over little c. So what we do here is we multiply by C both sides. So we get K is equal to C sine of B. Multiply by B on both sides for this one, and we get K equals B times sine of C. These two together, we can set them equal to each other. So if K is equal to C sine B, and K is also equal to B sine C, that must mean that C sine B is equal to B sine C. We divide by C and B on both sides. So if I divide by C and B on both sides, C's cancel here, only B's cancel here, then you're left with what we want. Sine B over little b is equal to sine C over little c. And that completes the proof, because if sine A over A is equal to sine C over C, and sine C over C is also equal to sine B over B, then all three of those things are equal to each other. It's got to be. So there's our proof. And that's the proof of the law of sines for the acute triangle case. For the obtuse triangle case, it's the exact same work. The only difference between the acute and the obtuse triangle case is that the altitude on one of those angles is going to be outside of the triangle. But it's the same idea. So we won't go over that case. We'll go straight into an application of that to solve. So here's law of sines two different ways. And they wrote it in a way that was different than the way that I wrote it. Some textbooks do it with the side lengths on top and the sine of the angles on the bottom. The way that I normally write them is the angles are on top and the side lengths are on the bottom. Doesn't really matter. It's the same for both. You can cross multiply and solve, and you can get either or, no problem. So here they give space for the alternative form, and to me it's not an alternative form, that's the primary form for me. Sine big A over little a equals to sine B. They didn't even write it in, they're making me write it in. But it's the superior way in my mind. Angles on top, sides on the bottom. So example 1. Solve triangle ABC if angle A measures 28.8 degrees, C measures 102.6 degrees, and little c, which is opposite of big C, has a side length measure of 25.3 inches. So I'm going to want to draw this. And this is an obtuse triangle. So maybe we could draw it like this to draw an obtuse triangle. So I'm really bad at drawing obtuse triangles. Okay, so I kind of had to redo that over and over, and I just edited out the other attempts until I had something that I was semi-okay with. So even this I'm not okay with. I don't really care. So I'll call this one A and this one B. So what am I being careful with? I'm trying to be careful with the obtuse angle, the 102.6, so that one definitely has to be C. So this one that's visually obtuse, that one's definitely going to be labeled C. And I'm looking at 28.8. I'm thinking that's the smallest of the three. So I tried to put that up at the top because that one looks smaller than the other one. Okay, so what else did they give me? They gave me that side length C, 25.3 inches is the measure. They told me that this angle's 102.6 and then this angle's 28.8 degrees. So I'm going to go ahead and get my calculator ready because I'm probably going to need to be using inverse trigonometry. And we'll see why. So we'll start off here, 28.8, 102.6. Is there anything here that I could figure out using prior knowledge about triangles here? And yeah, there is. So if you remember, the three angles in a triangle have to add up to 180 degrees, and that's freebie pretty much. So what you do is you take 180, subtract both of these, 102.6, and then minus 28.8. And in degrees, this angle is 48.6. Okay, so that's nice. I was able to figure that one out. So one of those missing pieces I was able to find out no problem. The other two missing pieces are going to be a little tougher. So we'll see how we can figure those out. So I would like to know measure little b and the measure of little a. And that's probably where the law of sines is going to kick in. So I would love to use a trigonometric ratio here, but this is not a right triangle, and that's where things start getting a little crazy. So I know for sure that the law of sines is going to help me here. So let's go with sine of, and I'm going to use C for sure. C over little c must equal to sine of, I'm going to start with A over little a because that's alphabetical. So I'm starting with C first, and I'm going to couple that with A first because A, that doesn't really matter. I could do A or B. So C first because they gave me both the angle and the side. So I have two. Those for sure I'm going to be using. So I have to use C because both the angle and the side are given. So I know for sure sine of 102.6 degrees divided by 25.3 must equal to sine of, in this case, A is 28.8 degrees. I don't know little a. So that's the one little variable right now in that equation. And there's only one variable there. I should be able to solve for a no problem by cross multiplying. So if I cross multiply, which I'm not going to show the details of that, you get a sine 102.6 degrees equals to 25.3 sine of 28.8. In order to solve for a here, you would divide by sine of 102.6. So a is equal to 25.3 sine of 28.8, and this quantity is going to get divided by sine of 102.6 degrees. So you got to make sure that your calculator's in degrees first off. Mine's in degrees. And when you plug this into your calculator, making sure that you're in degrees, you end up getting 12.48915 is what my calculator shows. And significant digits. 3 significant digits, or to the nearest inch, or the tenth of an inch, that is. So that's going to be 12.5. So 12.489 would round up to a 12.5. And that's inches. And that's what I'll label letter A with. That's 12.5 inches. Okay. How do I find the value of B in this case? So some of you might have the temptation to use the Pythagorean theorem. In this case, Pythagorean theorem doesn't work because we don't have a right triangle. So that would work if this were a right triangle. So unfortunately, I can't use the Pythagorean theorem. I'm probably going to have to use the rest of the law of sines. So I've coupled C and A together. Now I'm probably going to want to use sine of C over C and compare that with sine of A, or sine of B, sorry, over little b. since those two quantities are supposed to be equal anyway, now I'll skip through all of the algebraic junk, which we should be very comfortable with. B is supposed to equal to C sine of B divided by sine of C, if I did that symbolically. So you would multiply both sides by C, you would divide both sides by sine of big C, and then we just plug in. So B must equal to, little c is 25.3, sine of big B, 48.6, which we found by subtraction. And then that's divided by sine of C. So sine of big C, that's sine of 102.6 degrees. And I forgot degrees on 48.6. And then we'll go ahead and plug that into the calculator as well. So on my calculator, I could just, it's the same thing if I just changed out the 28.8 from the previous calculation to a 48.6. And we should be getting 19.446. Now that 4 isn't enough to round the 4 to a 5, so that's just a 19.4. So then B is 19.4 inches. So I could box this, and then what else? This one? Those are the unknowns in this case. Everything else was given. And that's it for this particular problem, example number 1. So a pretty simple case. So look at example 2, which is an applications problem. There'll be some of these on your homework. And this one's pretty simple because it's not actually an applications problem. They already drew the triangle for you, so I don't know if there's any other. There's one right here, which I want to go over example 3 for sure. So let me just double check. That's an angle, side angle. This one was a side angle, angle. So angle, side angle, angle, side angle. So if we know example 2, we also know 3 and vice versa. So example 3 is probably the harder one. So I'm going to go ahead and skip 2 and look at example 3, since they're the same type of situation. This one, we just have to actually draw it out ourselves. The bearing of a lighthouse from a ship was found to be north 52 degrees west. So we'll figure that out in just a little bit. So north 52 degrees west. So if I were to draw that, we start off with the north axis, and then we go towards the west axis, in this case, north, east, south, west. And it's 52 degrees this way. So that way this angle is 52. So that's the bearing. After the ship sailed 5.8 kilometers due south, let's see. Yeah, so the ship initially had that bearing to the lighthouse. And then the ship sailed due south. Find the distance. So the new bearing is going to be north 23 degrees west. Find the distance to the nearest tenth of a kilometer between the ship and the lighthouse at each location. So we have a ship. I'll call it S. That's the initial location. And there's a lighthouse somewhere. If this is the north axis, we go towards the west axis, 52 degrees. That's how we draw that angle given the bearing description. So that's a 52, by the way. So it doesn't look like a 52. So it's measured that way. And the lighthouse is somewhere out here. That doesn't tell us how far away it is. So this is the lighthouse. I'll call that L. After the ship is sailed 5.8 kilometers due south. And what does that mean? It goes in a straight line in the exact south direction. So that's south. It sails 5.8 kilometers this way. Find the distance. And let's see, before they say that, they tell us that the new bearing. So the new bearing from the ship to that lighthouse, if I were to draw this as a straight line to the best of my ability, it's not too bad. We can call this point, let's say P. And there's no alphabetical order in which I made that decision. So just P, whatever. So that's the new position of the ship. That new bearing should be smaller, we would imagine, geometrically. And it is north 23 degrees west. So this is a 23 degree angle now. And that's the only information they're going to give us. Find the distance to the nearest 10th kilometer between the ship and the lighthouse at each location. So each location meaning they want this one and they want this one. So I might want to use letters to denote each of those. That's opposite of side or angle S. I'm going to call this a little s. This one's opposite of angle P, so I'm going to call this little p. And this one's L, little l, which I'll use like a curly one. And I might want to move this because I need some space to do some work. So I drew that right down the middle. I might need this over here to the side. And then have all this space here for some work. So as you would probably guess, since this is not a right triangle, I might have to use a bunch of law of sines. So let's see. Can I luck out knowing other angles? I might be able to. I think I know how to find all of the missing angles. And how? I can find out this one no problem. The angle S. And why is that? Because I know that between north and south, we have 180 degrees. That's a straight angle. We used to call those straight angles in geometry. So if the terminal and initial side form a straight line, that's an angle of 180 degrees. So 52 subtracted from 180, let's see, 122? No, 128. 152 plus 128 is 180. So that's 128. And then I could use both of those, add them together, the ones that I do have, 23 and 128, subtract those from 180, and I can figure out L. So let me use a calculator for that. I'm not too proud not to use a calculator. So 180 minus, that's 151 combined. That's 29 degrees. So I have all three angles, no problem. So I was trying to look for like the low-hanging fruit. What's the stuff that I can easily figure out, no problem, without having to do some trig or some law of sines, stuff like that. So I think at this point, those are all my freebies. Now I got to resort to using law of sines. So how do I do this? Sine of, we're going to go with the ones that were given. They gave me the side length here, and then this one technically was given. So sine of 29 degrees divided by 5.8 must equal 2, and it really depends on which one I want to go with first. Let's go with S first, I guess. This must equal to sine of 128 degrees, because that's the measure of angle S. And then that's equal to little s. Cross multiplication, and then division a bunch of times. We get little s must equal to 5.8 sine of 128 divided by sine of 29 degrees. I'm still in degrees on my calculator, so I could just type that in no problem. 5.8 sine 128 divided by sine of 29. And I think I did that correctly. I'm getting 9 point, and again, it's two significant digits, 9.4. And I don't want to go with sig figs. I want to go with like nearest. Oh, did they tell me? Yeah, they did. They gave me instructions. So I have to follow instructions. Nearest tenth of a kilometer. So I was going with what I saw for the one that was already given, little L, 5.8. So I was going to use that same scheme, and I would have lucked out because it's the same as what they want. So little s, that's one of the ones they want. And then what else do they want? They want little p. So little s is the ship's current distance away from the lighthouse. What was its original distance away from that lighthouse in point S? So you would use sine 29 degrees divided by 5.8 again, because I'm using angle L, because that side was given. A thing that you should be noticing, so a recurring pattern, you start off with the two that you know an angle and an opposite side. And this is equal to, well, you want at least one of the others, at least one angle or at least one side, and you can solve for them no problem. So in this case, it's sine 23 degrees, which was given, divided by, well, I don't know the opposite side, little p. Cross multiplication, you get p equals to 5.8 sine of 23 degrees divided by sine of 29 degrees. That should be close to 5.8, because sine of 23 and sine of 29 aren't very different. .67. So 4.7 kilometers, because we're rounding to the nearest tenth of a kilometer. And that's the other bit of information that they were going to want. So much other than this, I don't think I'm going to go over. So that's example 3. I'm not going to give you too many out of this section. There's what we call the ambiguous case, which I'm definitely not going to go over. That's not something I'm going to require given these current circumstances. It's something I do normally go over and test anyway in both pre-AP and dual, that's one of those things I'm going to go ahead and skip. So I'm going to see if there's anything else I want to go over before we stop, which I doubt it. And no, because then there's the area stuff. So that's basically going to be it for this section. And we're going to go ahead and stop here for 8.1. 8.2 will cover the law of cosines, which for that one, expect a proof for law of cosines. And then we'll go over a couple of problems just like this one that we did here. We're not going to go over everything in 8.2 either. And that's it. So expect a homework assignment for 8.1 and 8.2 if you're in pre-AP. Expect a homework assignment for 8.1 all the way through 8.3 if you're in dual. Due by, I'm not sure, sometime this week.